Very much, Anna, and welcome everyone. Thanks for joining us. Today we're going to talk about building social games, and in particular the data layer considerations for constructing a social game that's capable of scaling. We'll go through four things here today. The first is a look at a game called Draw Something, and then we'll talk about NoSQL database technology generally. I'll do a brief introduction to Couchbase, and then we'll talk about another social game case study where they transition from MySQL to NoSQL database. They use Couchbase, and I'll actually use their slides that they presented at a conference to talk about some of the challenges that they faced and how they resolved them. So with that, let's get into the webinar. Back in February of this year, I wrote an article for Mashable.com talking about the same content that we're going to cover today in the webinar. And it turned out to be very timely. The topic was, just like this webinar, how to prepare your game for massive growth. And I argued that the data layer was a critical consideration in ensuring that your game was postured to scale, and that scaling was a critical success factor because these games can grow virally and unpredictably. And just 5 days later, a game called Draw Something was launched by OMG Pop. For those who don't know what Draw Something is, you draw pictures, very much like a game called Pictionary. You send them to your friends. They try to guess the word that you've drawn. The game launched on February 6th, and on early March, around March 1st, there was an episode of Jersey Shore, U.S., really horrible piece of television, but Jersey Shore featured, or at least exposed Draw Something. And from that point forward, the game grew virally. A singer in the United States, Miley Cyrus, tweeted about it, and the game went off the charts from a popularity perspective. It was the fastest growing mobile application, not just game, but application in Apple App Store history. And in concert with the growth of downloads, which reached 30 million by March 29th, the data that was being generated and stored by the game was growing even faster. There were, on March 29th, when 30 million downloads had been hit, there were over 5,000 drawings being stored every second. 2.2 billion drawings were stored at that point. 105,000 database transactions every second, and over 3.3 terabytes of data stored. So massive growth from a database perspective to match the popularity growth of that game. And they were successful in keeping up. There was never a moment that Draw Something was offline. The game stayed up and running consistently from February 6th all the way through this point, and has continuously since then, as a matter of fact. And that is in very stark contrast to another game that was launched just about the same time Draw Something was going viral. So on March 1st, when Jersey Shore was tweeting about Draw Something, The Simpsons Tapped Out was launched. And it began to grow at the same pace that Draw Something was growing. In fact, it was outpacing Draw Something at the launch. Unfortunately, just 5 days later, EA, which was the publisher of the game, had to pull the game from the App Store, and it is yet to return. And it is scaling challenges that led to the takedown of that game. And so we've got this, very stark contrast between what it looks like to have prepared for growth in the face of viral growth, and what it looks like to have not prepared for growth. And again, incredibly timely, and a foreshadowing of what we're going to talk about today. So let's talk about NoSQL database technology and what it provides for, why it was invented, and some of the challenges of adopting it. So if you look at a typical interactive software system, a social game, and you look at the architecture, Typically, you've got client-side applications. In a typical social game, perhaps it's a Flash-based client-side component running in a browser, hitting a load balancer, fanning out to a collection, perhaps Apache PHP servers. And on the back end, frequently what we find is relational database technology with perhaps a Memcached D tier sitting alongside that. Now, huge sort of striking difference between both the scaling model and the cost economics between the application logic and the database tier. So if you look at this application logic tier, beautiful ability to continue to cost effectively maintain performance in the face of scaling. So the scaling model is, if I have a lot more users that are putting pressure on my logic tier, I rack up, one more Dell box or whatever flavor of server I'm using, or I spin up another EC2 instance, update my load balancer, and suddenly I've got additional capacity. And so I'm able to maintain, in the face of user growth, application performance almost indefinitely. And the cost structure associated with that is this nice sort of linear increasing model. 1,000 more users, one more AMI or EC2 instance. Another 1,000 users, another box. Another 1,000 users, another box. And so very predictable and easy to keep up with growth. I don't need to over-provision. I don't need to worry about under-provisioning because it's so easy to scale. Now, the database tier, using relational technology, it's very different. If you look at the performance curve, actually, let's look at the cost curve. So the cost curve tends to be, from a scaling perspective, as you're growing to serve more and more users, sort of monotonically increasing nonlinear function, because instead of throwing one more server into the rack or spinning up one more EC2 instance, you tend to have to get a bigger box. Relational technology is a shared everything technology. It assumes that memory and disk is available to the database, and it's not a distributed technology. And so highly engineered boxes like Sun, E10K, E15K, or very complex, highly engineered servers are needed to scale up. You don't get one more box, you get a bigger box. And that gets more expensive on a per MIPS basis. But the bigger challenge is that at some point on the performance curve, you end up hitting a wall. You just can't get a bigger box at some point. And that ultimately ends up being the big challenge for virally growing social games. Now, there have been many attempts to extend the scope of relational database technology to keep it relevant and to address some of the shortcomings. Some of those include data partitioning. Rather than using a single database, I will manually shard or horizontally partition or vertically partition my data set. I will, for example, take users in Europe and put them on one database, and users in North America and put them on a separate database. As I have growth in Europe, I may split between Northern and Southern Europe. And so I begin to shard my data and split it across servers. The challenge is that it's very disruptive to shard. It impacts the application. You have to know that now I'm going to go to this other database in order to look up records. Schema management, if it was hard on a single server, becomes very difficult on many servers. Another tactic is denormalization to increase speed. Rather than strictly normalizing the database, I will repeat data, which allows me to look it up faster, to minimize locking, and gives me some flexibility with regard to the data that I'm storing in each record. At the limit, many organizations, Zynga is one of them actually, end up using relational technology just like a key value store. Rather than having a schema that's complex and normalized, I'll simply store key value pairs inside of MySQL, for example. It gives me a lot of flexibility. I can change at any point in time when I'm storing in the value. The challenge is that I give up just about all the benefits of relational technology. I can't query, and so a huge trade-off. But if relational technology is all you have and you have to scale, it's an effective approach, at least for storing your data. And then finally, distributed caching. Memcached is almost universally deployed alongside relational technology when it's used in social gaming environments. It accelerates reads, really doesn't do anything for writes. It does provide you with some scale-out capability alongside a non-scaled-out component in the relational database. But the big challenge, and just to talk about Zynga, which their architecture prior to adopting NoSQL technology was Memcached plus MySQL. The big challenge they had was that it was yet another tier to manage, and it became very expensive. When Couchbase was deployed at Zynga on their first social game, they had 600 nodes of Memcached deployed alongside 300 nodes of MySQL. So two very large infrastructure components, both requiring management and not doing anything for write performance. So to deal with that, NoSQL database technology has been created, and it takes the same approach at the data layer that just about every application at this point is taking at the application logic tier. A NoSQL database technology is built to scale out versus scaling up, automatically spreading data across any number of servers, and at the limit, providing the same scaling and cost benefits that one obtains at the application logic tier. It's a harder problem to solve. Typically, the application logic tier is stateless. These applications are designed such that any request that comes in through the top can be routed to any particular server or any one server in the application logic layer. And it's possible to do that by sharing data down here at the data layer. The problem at the data layer is that it's anything but stateless. It's where the state is stored. And so you have to account for the fact that data does live somewhere, and you need to route those requests to the right server. If those servers die or if they're unavailable, you have to be able to account for that and reroute requests. And so it's a very complex problem, but it's a problem that's been addressed quite well by NoSQL database technology. Now, interestingly, we did a survey back in December of last year, and we tried to make this very broad. We went out and asked on many, many websites and in many communities people to participate in this survey. And one of the questions that we asked was, what is the biggest data management challenge driving your adoption or your consideration of NoSQL technology? The interesting part is that the things that we've been talking about here, inability to scale out data and the ability to maintain performance, came in at number 2 and number 3. The most interesting, or the highest driver, if you will, of NoSQL adoption was not those two, but rather the ability to eliminate schemas, to change your mind about the kind of data that you're storing in the database, and therefore to get a lot more flexibility in the application development process, the ability to add more features more rapidly without having to deal with the challenges of schema management that one faces in relational database technology. And this was surprising, actually, information to us. When most people began developing NoSQL database technology, these were the problems here that were being addressed, scale out and performance. But over time, as people have adopted the technology and considered the technology, it's become pretty clear that flexibility, while it's a softer value point, it's clearly viewed as critically important. We'll talk about that more in a minute. So let's talk about a taxonomy. So what I'm going to try and do here is, in as neutral a fashion as I can, describe a taxonomy for thinking about the types of NoSQL database technology that are available in the market today. So if you get down to the core of all NoSQL databases, what you find is a key value store. Right? So a key is just a primary key representing an identity for a given record in the NoSQL database. And Associated with that key is simply a blob of information, some opaque binary value that's associated with the key. Every NoSQL database at its core is a key value store, and what we'll see is there are varying degrees of ability for the database logic to peer into that value and to act on that value. Different ways of considering what the value is and being able to operate on that value on behalf of an application. But at its core, key value is present in every NoSQL database. And Memcached really is sort of the canonical example of key value technology that emerged very early in application development. Memcached is a distributed cache. It's a key value cache. It allows you to add many servers into a cluster, distribute these key value pairs in main memory, and it's a very simple to use technology. There are very few operations that the cache supports. There are about 11 verbs, but typically you just put data into the cache and get it back using set and get operations. So I can say, here's a key, here's a blob of information, please store that for me, Memcached, and I store it in one of the servers in the cluster, and when I want that information back, I simply get it, and I've got the ability then to access that information from any application server on top. Very simple, very fast. Some of the challenges associated with Memcached are certain, it's a cache, and so if you need persistence of data, you need to ensure that your data is going to be there through power loss or through disaster. Certainly Memcached needs to be paired with a database. One of the challenges with Memcached is that applications grow very dependent on it, and if you lose a node in Memcached, you lose a chunk of your data, 1 over n, of the data typically, where n is the total number of servers in the Memcached cluster. And that forces a lot of rereads from the database server, which can grind many applications to a halt. In addition, adding and removing capacity or adding capacity to a Memcached cluster can be very disruptive. Notwithstanding that there are techniques used to ensure that data doesn't have to move around too much in the Memcached cluster, some data will have to move. And if enough data moves when net new nodes are added to the cluster, you can get back into a cold cache situation where a lot of refills need to occur out of the database, again, grinding a lot of applications to a halt. So it's great for accelerating reads, but it's certainly not a database replacement. Rather, it's a companion to database technology, as we described earlier. Redis is it sort of builds itself as a better Memcached than Memcached. And it's a very cool system. And in fact, frequently we'll see at Couchbase, Redis oftentimes deployed alongside Couchbase to serve certain parts of the application logic requirements. So Redis is very much a key value store, but it provides a lot of operations that are specific to certain types of values that one can store. So for example, you may declare that a given key value pair, the value part represents a list, perhaps a list of game players. I've got player 1, player 2, player 3, and some of the operations that are available from Redis include things like, if I know it's a list, add a new player to the list, remove a player from the list. Take 2 lists and tell me what the intersection are of those 2 lists. In addition, there are sets, there are hashes, there are strings, sorted lists. So basically, Redis declares that it knows about a number of data structure types that can be represented in the value payload in these key value pairs, and it provides a whole host of operations that are specialized to work on those types of values. So you can get a lot of flexibility, you can get a lot of work out of the database that you can't get out of a key value store. So with Memcached, for example, if I want to maintain a list inside of Memcached, if I want to add something to that list, I need to read the entire key value pair over to my application logic, look inside of the value, add or remove a list member, and then restore that value back into Memcached. With Redis, I simply tell Redis itself to add something to the list, and it's atomically done without doing a transit of the key value pair across the network. So very flexible for certain data types, but again, this is really caching technology with specialized operations. But again, a lot of value add above and beyond simply key value technology. So we're starting to develop this catalog here. So if you look at the top, we've talked about strict key value technology. We've talked about Redis calls itself a data structure server. So taking key value and adding a lot of knowledge about what's inside the value and capabilities, but we're really talking about caching technology here. So what we're going to do is move on toward database technology and begin to get even more sophisticated relative to treatment of the values in these key value pairs. So Membase was a technology that was disk-based. It was very much like Memcached. Key value technology, opaque binary value. The set of operations was equal to the set of Memcached operations, and in fact, it was a drop-in replacement for Memcached. It allowed you, however, to not only store data in RAM, but also on disk, and it provided for the ability to add and remove capacity from the cluster non-disruptively, so there was never any cold cache situation, and if the cluster was lost, it was able to restart, reload data. And so it was very much a database technology that had the same semantics and same operational capabilities as Memcached. Zynga deployed initially Membase to replace their MySQL plus Memcached clusters. And so it's a database, key value semantics, and providing for ultimately the ability to collapse those two previously discrete tiers into one, massively saving costs, both on the capital side because you're combining these servers, and on the operational side because you've got only one tier to manage. Now, Couchbase is an extension of Membase and was created by combining the clustering capabilities and the caching and performance capabilities of Membase with the indexing and query capabilities of CouchDB. So Couchbase, just like every other NoSQL database that we'll talk about, is a key value system. But if the value is in JSON format, JavaScript object notation, the database is capable of indexing, performing MapReduce operations, and responding to queries. And so it's a document-oriented database. It's kind of a confusing term. It really doesn't have anything to do with documents as one would normally consider them, you know, Word documents or PDFs or documents like that. It really is more of a semi-structured database. JSON is the format that Couchbase understands. We'll talk about MongoDB, which is BSON format. There are XML databases. All of these are document-oriented databases. Couchbase, though, is designed to be a sharded, distributed, high-performance via built-in caching technology document-oriented database, and it slots into our taxonomy here, and we're showing that it really was an extension of Membase into the document-oriented arena. MongoDB is another document-oriented database. It is also disk-based and provides a form of in-memory caching using memory map file technology. Versus JSON, MongoDB uses BSON, which is sort of a binary version of JSON that they created. And it is a technology that supports ad hoc queries. You're able to query anything that's stored in MongoDB without previously defining any sort of indices, but it's certainly best from a performance perspective when it is indexed. And it slots in here in the document-oriented column with Couchbase server. Now, there are two other types that we'll talk about here. So Cassandra versus a document-oriented approach. If you look at a typical key-value pair in Cassandra, the way that it works is it defines columns. So you're able to take a value and declare that certain areas in that value represent columns of data. And the database uses a different approach in that it is an eventually consistent system. So Cassandra allows you, just like everyone else, to take a key value pair and layer on top of that some sort of understanding of what's inside the value. Here it's columnar forms. And it's flexible in that not all rows must have all columns, so you've got the flexibility benefits that are part and parcel of NoSQL database technology. One of the challenges with Cassandra, though, is that it is an eventually consistent technology, which means that when you store something in the database, it takes some period of time before that particular stored data item is replicated across the cluster, and during that period of time, some application nodes can get answers that differ from the answers that other application nodes may get. And so the developer model is a little more complex than an immediately consistent system like relational database technology or some of the other systems we've just described, in that you have to be prepared in your application logic to deal with the fact that data will not be, that readers may actually get something different than what was most recently written. But other than that, it is a NoSQL database system that provides for clustering, the ability to add and remove capacity. The challenge, again, being the developer model is somewhat different, and performance has historically also been a challenge. Cassandra is known to be a system that can ingest large quantities of data. It's very write efficient. But for random reads, it is less performant and frequently deployed alongside caching, very much like relational database technology is today. There's a specialized technology, graph database technology, that is frequently sort of lumped into the NoSQL class of technologies. Graph database technology has actually been around for a very long time. It is different in that you've got key opaque binary values to these key value pairs, just like all the other systems, but there are relationships that exist. And when these relationships are in graph form, the system has a number of very specific operations that it can do to traverse down to leaps, to insert and to remove nodes, and ensuring that when those nodes are removed, that the children are reformed to the upstream nodes. And so if you've got graph-oriented data, where you've got graph-like relationships between these key value pairs, systems like Neo4j, which is the canonical example of graph database technology, are very appropriate and quite useful. It does turn out, though, to be a reasonably specialized technology. It's not as general purpose and as flexible as, for example, document-oriented database technology, and it really is appropriate when you've got data that is very graph-like in nature. And so that's it from a taxonomy perspective. In the article that I talked about earlier that's on Mashable.com, I made an argument that document-oriented database technology it provides a very good trade-off between flexibility, performance, and cost. And if you look at the landscape of social games, what you find is that Couchbase and actually to a lesser extent MongoDB tend to be the dominant NoSQL database systems that have been used. We've got literally dozens and dozens of social games, including those from Zynga, Disney, and OMG Pop, now a part of Zynga, and many, many others that are using document-oriented database technology, specifically Couchbase, because it does provide a really good sort of cost-benefit optimization for this given use case. And we'll talk about that as we go through our final use case. So Couchbase, looks just like the slide that we talked about earlier, that we displayed earlier, where you've got a set of users up here in their browser using Flash-based technology, coming through a load balancer, fanning out to a collection of application servers. Couchbase, because it is Memcached compatible, allows any Memcached library to talk to the Couchbase cluster. However, we also make a set of language-specific SDKs. Today we have those for Java, .NET, Ruby, PHP, Python, C, C++, and so a wide variety of support for application logic. And at the bottom, at the database tier, Couchbase exists, and again, you've got the same economics and scaling properties that one gets on the scale-out tier of the application layer. Talk a little bit about how it works. So Couchbase distributes documents or records across the cluster evenly. And in addition to maintaining the sort of the active master copy of the data, Couchbase also, I can get this thing to go forward. I hate build slides. Okay, Couchbase also provides, well, it's not going to work on building here, so I'll just go to the end state. So Couchbase also stores replica documents. So if you look at a set of active documents that live across the server, in addition to those, each node maintains replica copies of the data, and you can configure Couchbase to store any number of replica copies. So here we simply have a single replica, and you can see that for document number 5 stored on server 1, there is a copy of document 5 stored on server 3. The application doesn't have to know anything about where replicas live or if they live. It's all transparent to the application. The application simply stores the data. The Couchbase client library knows which server is to store document number 5, directs the write and read operations to that server, and to the extent that there is a server failure, as we'll see on the next slide after the next one, if a server fails, replica documents are promoted, and the application's automatically redirected to the server that now contains the master copy. We'll show that in a second. But from a basic operation perspective, an application, the logic, let's say PHP logic, lives up here in application server number 1. It stores, it simply says store the data in Couchbase. The Couchbase client library, the Memcached client, knows then to go to server number 1, for example, if it was document 5, to store that data and then later to read it back. So for the application developer, it's very simple. It looks like one database in the client library. You simply read and write data, and Couchbase takes care of directing those operations on the back end to the appropriate server in the cluster. So, okay. If you add nodes to a Couchbase cluster, so here we are showing that same 3-node cluster, and if we want to add servers to that cluster, I'm still having the same challenge here trying to move through these build slides. Okay, so let's, here we've shown that we have added server number 4 and number 5 to the initial cluster of 3. What you didn't see is that as Couchbase was previously reading and writing to these 3 nodes, when these servers were added to the cluster, a rebalance operation was triggered. So with Couchbase, you're able to add any number of servers that you want to a cluster. Once you've added those servers to the cluster, then you say that you want data to be redistributed across the cluster to include those net new nodes that were added. So even as the cluster is up and running and the application is accessing data on the back end, Couchbase, once that rebalance operation is initiated, moves the data from the old servers to the new servers, evenly distributing the information across all of the servers, and it does it in a way that is completely non-disruptive to the application. So reads and writes continue to occur up top, data gets moved effectively out of the back end, and once the data has migrated to the net new servers, they are put online. The cluster map inside of the Couchbase client libraries is updated, and now data operations, reads and writes, are redirected to the net new servers, again, without ever impacting that live application. Going back to the OMG Pop Draw Something example that we opened with, this is what allowed them to continuously add capacity to their Couchbase cluster without taking the game offline, without impacting what was ultimately viral growth that led to their success. So with that, let's talk about Tribal Crossing. So I'm going to use slides that they actually created at Tribal Crossing and presented at a conference several months ago, and do my best to communicate what they were kind enough to put together and make available publicly. So Tribal Crossing is a Facebook game by Fable Labs hosted on EC2. It is sort of part Pokemon, Frontierville, and Mario Galaxy. It allows you to basically raise plants and interact with animal types across this virtual world that they maintain. The challenges that they faced were scaling relational database technology. They were challenged tuning their queries. They were dealing with denormalization in order to get performance, but as a result, struggling from a query perspective. They were caching their data, as most people do with relational technology, using Memcached in order to accelerate reads. They were challenged with replication, configuring and maintaining read slaves, and in general, tuning MySQL to ensure that it was going to provide the kind of performance that they needed. And they were concerned about scaling, as they were already experiencing challenges maintaining their data layer. They were very concerned about the implications of success and wanted to ensure that they were prepared to the extent that the game took off and gained a wide audience. Some of the challenges that they wanted to be able to address, or some of the properties of their environment, they had a very write-heavy environment. There were changes being made constantly to game state as a result of play. They needed to scale and were burned by the addition of a capability called MyPolls that went from 100 to 1 million users over a weekend. And that created a lot of challenge for them. They wanted to keep their costs down, and they didn't want to build a big team of system administrators that were experts in tuning and caring and feeding for MySQL. They looked at a number of options. So they were using previously MySQL with master-master replication sharding and Memcached. We talked about the challenges associated with that. They considered Cassandra that we talked about earlier, a column-oriented database that provided them, and in their benchmarking with good write throughput, but low read throughput. There were some complexity concerns with regard to reconfiguring and rebalancing the cluster. And we talked about previously the eventually consistent model that Cassandra provides, which was deemed too complex and burdensome for their application developers. So I ended up passing on this. Considered MongoDB, which was a high performance on both random reads and writes, but unpredictable in the latency of reads, and in part due to the architectural model of MongoDB, where you've got far less control over the data that sits in memory than you do with, for example, Memcached, where it's a managed caching environment with the ability to eject data in a very systematic way to ensure that only the freshest data remains in memory. At some point with MongoDB, when you reach certain memory thresholds, you end up thrashing memory pages, and latency sort of falls off the cliff, and predictability was critically important to their environment. Live cluster rebalancing didn't exist for adding and removing nodes. It only worked on existing nodes. And they had concerns about the data storage model. And so they ended up picking Couchbase. Performance was one of the key considerations. Couchbase provides very predictable, very repeatable, high-performance random reads and writes. Typical, so on a 3K object payload, a read on Couchbase will typically occur in about 800 microseconds with a standard deviation on both sides of about 200 microseconds. So it's both very fast and very predictable and repeatable. And that was very important in their environment, and typically will be for a social game where you know, the ability for users to feel like the game is responsive, where you don't have to wait for operations to occur, is critically important for the user experience. Couchbase also provides immediate consistency, so the application developer model is very, very familiar. You store something, and the next person that reads it is going to get just one answer, and that answer is what was just written, which is what most developers are accustomed to, you know, from their database. The interface was very, very simple to use. They, like most other people, were already using and familiar with Memcached, and so the ability to adopt the technology, and in fact in their environment to make no changes to the application at all to adopt the technology was available. Very low sysadmin overhead, schemaless data store, use and prove, et cetera, et cetera. And one of the interesting things to note is that making the shift to NoSQL database technology is non-trivial if you have a very large base of code that has been built around relational technology. So it was easier for them to adopt Couchbase, or frankly any NoSQL solution, because they were in a development mode where they didn't have a large legacy code base that was highly dependent on the relational model and structure. So they didn't have to do a bunch of rewrites of application logic in order to adopt it. Now, there were some challenges. The biggest difference is that in Couchbase at the time, which was release 1.7, now release 1.8, that has the same property, there was no easy way to query data. So Couchbase 1.8, the current release, provides the same key value operations that one gets out of Memcached. There is no query interface. Now that gets resolved with Couchbase Server 2.0, which is currently in developer preview 4 and scheduled to ship in a couple of months. So that challenge is resolved, but nevertheless, the current production shipping version of Couchbase does require one to think differently about queries and the storage of data, and we'll talk about that in a second. And the way that they dealt with it was by sort of breaking out of this ORM relational paradigm that's, you know, that most application developers are accustomed to. And we'll talk specifically about how they structured their data and the types of operations that permitted them to build this very complex game and reasonably complex data model using simply key value operations. So the deployment of Tribal Crossing was done, as I mentioned earlier, in EC2. You can look at their architecture using Apache and PHP, along with what's known as Moxie on the client side. Moxie is a proxy technology that can sit between application logic that knows how to talk to Memcached and provide the ability to route those requests to the appropriate Couchbase cluster without having to do anything to the application logic. So using a simple Memcached client, not changing a line of code in the application, Moxie allows you to provide for both persistent connections to these backend Couchbase servers, as well as deal with changes in cluster configuration in a non-disruptive way. If you look at the bottom, deployment of Couchbase in their environment, so they were using Linux AMIs, 64-bit versions backed by EBS. They configured swap space, did an install of Couchbase, pointed their browser at the host name that they configured in a DNS server, started up the cluster, and simply added more nodes to the cluster and rebalanced as they went. So the point here being that it was really, really easy. So Couchbase is a very simple system to install, configure, and to get up and running. It's a packaged software system that includes a very easy-to-use administrator console that's accessed via web browser. It's also completely scriptable. But unlike other systems that are, in many cases, very complex to install, configure, and administer, Couchbase was very easy for them to get up and running. Talking about Moxie, so Moxie is an intermediary that was installed on each of their web servers that allowed them to interact with Couchbase without requiring any changes to the application logic, and while allowing the addition and removal of servers in a non-disruptive way. So without taking the tribal crossing game offline, the ability to add and remove cluster capacity in a way that is transparent to the live running application was permitted by their use of Moxie. Now, we have smart clients available for both PHP, Ruby, and, as I described, several other languages that completely obviates the need for Moxie. And so if you're building a net new game, simply choosing our PHP or Ruby or Python SDK in the client library that comes along with it removes the need to deploy something like Moxie. But if you already have an application that exists and is using Memcached and has Memcached client technology, Moxie allows you to make absolutely no changes to the application while still enjoying all the benefits of Couchbase. So game data representation and tribal crossing. Here's a very simple simplification of their data model. Basically, players can have a variety of plants on their farm. They can add and remove plants, and they can see which plants exist on other players' farms. And obviously, it's far more complex than that. But just to sort of key in on one component of the data model, let's talk about how they modeled this using Couchbase Server. So in the application logic, you can simply treat these objects as maps or dictionaries or JSON objects. A key is paired with each of these data structures. In their case, they determined the key using a class name for the plant type and generated a unique ID that was associated with that given plant type. Now, they represented these objects as lists inside of the value, denormalized and comma separated, or they used array technology with the object IDs. So here we're showing three particular data structures: a player with a JSON representation of the properties of a given player, ID, the numerical ID and the name of a given player, a plant list that would be associated with the given player, which includes both an ID and a list of plants that exists inside of the given player's farm, and a plant object, which, very much like the player object, included an ID for the plant, a numerical ID, the owner of a given plant, and the name of that plant. So you can see that versus a relational model, this is very denormalized. You don't have, for example, a table of plant name types that are referenced from here to there. There is some data duplication, but it provides for the ability to very easily move data from one point of the cluster, one node in the cluster, to another in a way that doesn't require locking, doesn't require any of the performance and scalability limitations that are inherent when you have a highly normalized interdependent set of objects. So the benefits, of course, are no need to alter table. You can add and remove field types from any of those objects at any point in time. Gives you a lot of flexibility to change the data model, to change the kinds of operations and the functionality of the application when new data types are required. The key thing here, though, is to use JSON for your data objects. So JSON formatting, if you store your values in Couchbase in JSON form, you have prepared yourself to both index and query the data in Couchbase 2.0. And most application developers and social game developers at this point are using JSON technology anyway to ensure that A, because it's a standard, and B, to ensure the ability to manipulate that data using external tools, Couchbase being one of those. So accessing game data, if you look at a typical request, so this is an ASCII version of the request as it transits the network to retrieve a given player's information out of the Couchbase database. And if you look at the logic inside of the application, very simple. So simply create a new object, a plant list type, and then for each plant that's inside of that given type, you can add the plant to the player's object. To give a player a new plant, again, create a new plant object and simply set that plant into the given player's plant list, and then store that information back into the Couchbase server using a simple set operation on a Couchbase client object. So very easy to add and remove information from the player objects and then to update those in the database. Now, one of the challenges with NoSQL database technology is the ability to deal with concurrency. If you've got, for example, a number of application servers that may interact with the same record type or the same record or the same document, the ability to ensure concurrency without having conflict is a requirement. And there are two ways to do that with Couchbase. One is optimistic, the other is pessimistic. So check and set using CAS operations is the optimistic way. If there's a low probability that there will be a conflict, it's the appropriate way to interact, where you basically read a record or read a document from the database, update it, and then when you try and write it back, you use a CAS operation, which will fail if the data has been changed since it was read. So when you do the read initially, you're given an ID or a number, a cookie. When you set back into the database or write back into the database, you provide that cookie again, and the database will fail if the cookie is changed, which means the data is changed in the database, at which point you can reread and retry. So it's optimistic, it's fast. You do the read, you do the change, and you write it back. If it's changed, it fails. But if there's a very low probability that someone will have changed that data in the intervening period, it's a very fast operation. There's also support for locking, however. So if there's a high probability that a conflict will arise, one is able to read the data and lock it to prevent updates to that data while the update occurs on the application logic side. That lock is released once the write occurs. Now this is useful for perhaps locking down a number of objects that will that are interrelated, where you need to update all or none. And so you've got the ability to create synthetic transactions using GetL, where you can take these inter-referenced objects, update them, and then ensure that they all get updated or that none get updated using this capability. One of the important sort of data model aspects or considerations was the relationship of data items. So one of the things that they've done at Tribal Crossing to ensure that there is good referenceability between the objects is to do bidirectional referencing. So, for example, with their plots and plants, the plot object always stored the plant that it was hosting, or the plants that it was hosting, and the plant objects also referenced the plot that they were growing on. In case there was a mismatch, it provided the ability to recognize that a change had occurred, or that there was an inconsistency in the data, and the ability to then go back and correct that. So it provides yet another way to provide for cross-referencing. If you don't want to use GetEll, if you don't want to use CAS operations, and you want to be really aggressive, this provides for yet another mechanism for detecting conflicts and to provide fix-ups. Now, another capability of Couchbase is the ability to do multi-get. So you don't have to do lots and lots of transits of the network individually. You can do a multi-get where multiple reads will be packaged up on the database side and transited to the application in a single hop or a single read across the network. So moving on now to their migration considerations as they move from MySQL and Memcached. The first thing that they did, because this was an existing application using MySQL and Memcached technology, was to pick and choose the parts of their application or their data that were most that would be most beneficial or most positively impacted by this migration. So initially moving their slowest performing tables and the fields that were most frequently updated from MySQL, the write-heavy components, where they weren't getting the benefits of acceleration because of Memcached. You can look at their deployed environment. So in their case, initially running an 8-node cluster. One of the interesting things to notice here is that Couchbase does a really good job of evenly distributing the data across the cluster. So this was without any participation from the application, and through a very efficient hashing algorithm, Couchbase ensures that the data is evenly distributed using CPU, memory, and disk resources across the cluster very efficiently. You can see here, if you look at a week-long view of the operations occurring on their cluster, it's like many games. They've got a reasonably predictable pattern of utilization, sort of following sunrise and sunset across the globe. Typically seeing a lot of the use, interestingly, both sort of during work hours and then later during late evening hours tends to be where their application is most utilized. And in conclusion, as a result of this migration from Relational plus Memcached to Couchbase, they dramatically reduced the cost of both scaling and managing their database servers. They got significant improvements in performance metrics across both reads and writes, more predictable latency. Because Couchbase is so easy to use, they were able to focus a lot more of their energy on game development and optimizing their key application metrics, less time on struggling to ensure the database was up and running. And certainly they plan to use our Couchbase Server 2.0 MapReduce querying and indexing technology, which will be a big improvement over the simple key value operations that you're using today. And with that, if you have any questions, please send those to info@couchbase.com, and I'm going to open up the question and answer panel now and try and pick a few. We're at the top of the hour already, but let's look and see if there are any questions that I can address on the call right now. So there are none in the question box, and there are none in the chat box. So if there are no questions, again, info@couchbase.com. We'll be happy to address those. And with that, I'll close the webinar. And thanks for attending.